Key features of the exponential function. In this first slide, I have information about two different types of exponential functions. The one on the left-hand side is our exponential growth function, and the one on the right-hand side is our exponential decay function. Now they look very, very similar. The difference is the end behavior. On the left-hand graph, our growth graph, you'll notice that as the x values increase, the y values are also increasing. So it's going up and to the right. And on the exponential decay, you'll notice that as the x values increase, the y values are actually approaching 0. So you'll notice that they do not go into the negative y values, but they level out and have an end behavior of approaching 0. So what makes these two differences is the base number. For growth, our base number is a value greater than 1, and for decay, it is between 0 and 1. If you look at the equation line down below, we have our b value is greater than 1 or between 0 and 1. Now let's look at some of the key features here. For the domain of both functions, our graph is all real numbers. For the range, and we're talking primarily for our parent function, so we have not applied transformations yet, the range are positive y values. Our intercept is whatever our a value is, and our a value is that vertical dilation, and our asymptote, so that line that the graph approaches that creates the shape of the function, is actually our x-axis. Our end behavior, as a reminder, end behavior talks about what are the y values doing in the graph as the x values get either larger or smaller. So the end behavior for our growth function, the function on the left, it says as our x values get smaller, the y values approach 0, and as our x values get larger, then our y values approach positive infinity. For our decay function, as the x values get smaller, the y values get larger and approach positive infinity, and as our x values get larger, our y values approach 0. Then we have two different models that we're going to work with a little bit later, our growth model and our decay model. Those you'll see when we're doing word problems. Now, like every other function that we've talked about this year, we graph them. And we graph them based on transformations that are being applied. So I'm going to highlight that base. So our base is part of our parent function, and the x is part of our parent function. Everything else would be identified as a transformation. In front of the a would be our reflection across the x-axis, and the plus or minus that is attached to the x would be our reflection in the y-axis. So remember that terminology that we've talked about before, inside of the parent function, outside of the parent function. Anything that is outside of the parent function changes our y values, and anything inside of our parent function changes our x values. Our a is our vertical dilation, so that would be a number multiplied by the parent function. Our b is our horizontal dilation, so notice that's on the inside and it's part of the exponent. Our h is our translation left and right. Our k is our translation up and down, and then we already talked about our plus and minus, which is our reflection. So if we're going to graph one of these, we look at the function that we're given. The x is in the exponent, so that means that we are graphing our exponential function. And we're going to just go through the process like we have for every other function that we've graphed. We're going to make a table of values. So we're going to pick x's and y's. I'm going to pick -1, 0, and 1. When we plug -1 into our equation, we get 2 to the -1. To simplify 2 to the -1, we take the reciprocal of 2 and we change our exponent to be positive. That's our negative exponent rule from when we learned exponents. If we put a 0 in the exponent, 2 to the exponent 0 is 1. And if we put a 1 in our exponent, we get 2. So we're going to graph these three coordinates: -1, 1/2, 0, 1, and 1, 2. Then we're going to make that shape of the exponential and join it up. So remember, if we go back to our key features graph, we have an asymptote that is the x-axis. So I'm going to actually graph our asymptote. Now our asymptote is going to change based on a vertical translation. So our asymptote will always be y equals, because it's a horizontal line, and it's going to be the value of k. Now because we don't have a number added or subtracted to our function here, then k is actually equal to 0. So in our case, our asymptote is y is equal to 0. The next part is asking for our intercept. So it's asking for our y-intercept because we have an asymptote on our x-intercept. If we go back to our key features, our intercept is 0, a, and a is our vertical dilation. So the important part here is that we can identify what a is. This is our base. That means that we don't have a number being multiplied in front. So it's implied that it is a 1. So our a value is equal to 1. So our intercept is 0, 1. Domain and range. Our domain is x is all real numbers, and our range is y is greater than 0. The y values are actually not touching that horizontal asymptote. The last part is our end behavior. So as x approaches -infinity, f of x approaches 0. So on the left-hand side, as the x values are getting larger, they're leveling out and approaching the asymptote of y is equal to 0. And on the right-hand side, as x approaches positive infinity, f of x is approaching positive infinity as well. So as the x values get bigger, on the right-hand side, our y values are also getting bigger.